Unit 2 Central Force Motion. What is a central force? A force is said to be central if it acts along the position vector of a particle drawn from the center of a force. For example, if F of r is a force, mathematically central force can be represented as F of r is equal to modulus magnitude F of r into unit vector r. This denotes the direction of the central force. Some examples of central force are Hooke's law of elasticity. We know Hooke's law of elasticity, F is equal to K into R. Second example is Newton's law of gravitation, F is equal to minus gmm by r square into unit vector r cap. Another example is electrostatic force between charges, Coulomb's law of forces, F is equal to q1 q2 by 4 pi epsilon 0 r square into unit vector r. These are some examples of central force motion. A force is said to be central if it acts along the position vector of a particle drawn from the center of a force. It should be noted that if the force is positive, that is, in the case of repulsive force, F is equal to positive, F will be positive, and F will be negative in the case of attractive forces. In the case of gravitational force, we know that there will be only attractive force, therefore it is permanently negative. Okay. Then this is a derivation. Central force motion is a one-body problem. Consider two particles of masses m1 and m2. Two particles m1 and m2 interacting each other under a central force F of r. Let r1 and r2 be the position vectors of m1 and m2 respectively. These are the two bodies m1 and m2. r1 and r2 are their position vectors respectively. The equation of motion, here it is O and this is point A, point B. The equation of motion for m1 and m2, we can apply Newton's second law of motion. Ma is equal to F of r, that is second law. m1 r1 2 dash 2 dot is denoting second derivative of position vector, that is acceleration. The equation of motion for m1 and m2, m1 r1 2 dot is equal to F of r into r, equation number 1, and that for the second particle m2 r2 2 dot is equal to minus F of r into unit vector r. Equation 1 by m1 and equation 2 by m2. Divide equation 1 by m1. This m1 will cancel, and equation 2 divided by m2 we will get r2 2 dash. It is r1 2 dash is equal to F of r by m1 into unit vector r. Put it as equation number 3. And r2 2 dash is equal to minus F of r divided by m2 into unit vector r. Equation number 4. Now subtract equation 4 from equation 3, that is r1 2 dash minus r2 2 dash. What will get? r1 2 dash minus r2 2 dash is equal to 1 by m1 F of r plus 1 by m2 F of r into unit vector r. It is equal to 1 by m1 plus 1 by m2 into F of r is common and it can be taken out. 1 by m1 plus 1 by m2. Here m1 m2 is the LCM here. Therefore m1 plus m2 divided by m1 m2 into F of r. Equation number 5. Now from this figure we can apply triangle law of vector addition. OA plus BA is equal to OA. OB plus BA is equal to OA. That is R2 plus R is equal to R1. Then R is equal to R1 minus R2. Here we can take second derivative, that is differentiating twice with respect to time. We will get R2 dash is equal to R1 2 dash minus R2 2 dash. Now look at equation 5 and 6. The LHS R1 2 dash minus R2 2 dash. Here it is equal to R dash, R2 dash. So we can equate, that is R2 dash is equal to m1 plus m2 by m1 m2 into f of r into unit vector r. Then this term is taken to LHS. m1 m2 by m1 plus m2 into r2 dash is equal to f of r. Put this m1 m2 by m1 plus n2 as a reduced mass and it is denoted by mu. Therefore mu r2 dash is equal to f of r into unit vector. This is similar to ma is equal to f. Therefore the two body problem is now reduced to a single body problem.